Yeah. All right, you got this.
All right. Hello. Welcome to Cryptography 1, which has been renamed from Crypto 1 because people got it confused with cryptocurrency. So hopefully no one is here with the wrong idea. And if you are here for cryptocurrency, maybe stay around for cryptography because it's just quite cool and interesting. So first things first, I passed my basic technological literacy exam.
Sorry, try it the other way. Not what I quite meant, but let me make sure you got the right arrow. Okay, no. Sorry about that. I hope it's not that. It's off! Sorry. There we go. All right.
Basic technological literacy test failed by me, but it's okay because I can still do crypto. Okay. So I'll give people a minute to type the meeting flag in. I hate to say it, but this is what happens in practice. You know, you'll learn how to don't rule your own crypto. You know, you'll learn the best ways to encrypt your stuff. But in the end, just be careful. If you have money, hire bodyguards. But this is an OPSEC. This is crypto, so we'll save that for another time.
Does that work?
Read it, yeah. All right, and as a reminder, the slides are available on SIGPwny.com/meetings. So I will move on, but if you didn't get a chance to put down the meeting flag, these slides are currently up right now. So, okay, so what is cryptography? At a kind of very high level, in the most general sense, we want to do secure communication, or I guess in the case of multi-party computation, maybe secure computation between two or more parties, because it's not really a party if you're by yourself. So typically we model these as Alice and Bob, and Eve as an eavesdropper. So we have some channel, Alice wants to send a message to Bob, and presumably the other way around as well. And how can they do this securely? You know, maybe you're worried your Harry Potter fan fiction, you don't want that getting out. I sure don't. Okay, so just to go over some historical examples of bad cryptography, because actually, over the years, I think it's had a lot more use in the information era, right? You all have computers, you're all sending, packets, doing multiple hops, probably, I'd say, like tens of thousands, millions of packets to a number of hosts all over the world. It's pretty important that you keep your packets secure. But historically, this is mainly used by, nobles, military generals, stuff like that, and we'll talk about military stuff a little bit later on. But I mean, previously, I think in the 16th, 15th century, Mary, Queen of Scots, was executed because the code she was sending to her conspirator/lover, I think. I don't know if I fully got that from Wikipedia, but that code was cracked and she got chopped. So hopefully that doesn't happen to you. The equivalent in this day and age of getting your head chopped off is having an attacker pop a shell in your system. So usually the bugs in OpenSSH are more, I guess, clone-themed bugs, like overflows and stuff like that. But there was a pretty bad issue several years ago where all of the default keys were not generated properly. It's bad RNG. And that was the point where they had to invalidate all existing keys, all default keys. So, yeah, so again, just to go over sort of then versus now historically, we sort of already talked about most of this, so I'm going to skip this. But the point I want to make is that current cryptography, we can't just say, oh, okay, we have a scheme, and because I can't break it, that must mean it's secure, because it's secure until it doesn't secure, and at that point, it's already too late. So we need schemes that are predicated instead on these hardness assumptions. And I'll talk about what that means in a few minutes. But essentially a hardness assumption means we're pretty sure this is hard. We have very good reason to believe that this is difficult to do. So that's what we try to build all crypto on now. Essentially saying we can't necessarily prove that this is true. Like if you could prove that P is equal to MP, well, actually, as it turns out, cryptography as a field basically goes away, at least about quantum computers. But you say, okay, if we assume that this is true, we have these things. And there's something called, in Pagliazzo's 5 worlds, people have added onto it by now, but sort of what cryptographic primitives hold in these different scenarios. Okay, so the main things, Crypto One this is going to be your toolkit, your survivalist guide for street fighting cryptographers. So probably the most useful operation we'll discuss today is called XOR. And if you've taken an ECE class or you do digital circuits or something like that, you're probably very familiar with this. But essentially, that's the truth table, right? So if you have a 0 or a 1, but exclusive. So if I have a 1 and a 1, that's a 0. But if I have a 0 or a 1, it's a 1. And if I have a 0 next to it, it's 0. So this is also basically the same thing as addition mod 2. I mean, not basically, like it is the same thing. And it has all these sorts of nice properties. It's as an operator, it's associative, commutative, it's its own inverse. If I take an operator XOR with itself, I get 0. Kind of for the same reason, if I XOR 0 with something, I just get that thing back. And as we'll see later, we're going to be using XOR. We have sort of an abstract ciphertext, plain text, or rather we have a key and a plain text, and we'll use that to get some ciphertext. Okay. And if you're following along, the order of these slides is not quite correct. But essentially, spoiler alert, you're going to want to install something called SageMath and PyCryptoDome. Pretty much all the crypto stuff is done with Python. So I'll have kind of more detailed instructions for how to download that. But when you're working in Python, generally speaking, you want to be working with bytes. So again, the 3 data types you'll have, integers sometimes, or a lot of the times, I guess, especially when you're doing modular exponentiation or things of this nature. Sometimes you'll have base64 encoded strings, there's a function for that, or otherwise you have a hex string. You can convert to and from all these things. And again, Stack Overflow is your friend if you're not sure how do you kind of juggle between these different types, but that's kind of a long and the short of it. Okay, so the first class of ciphers we'll talk about are something called substitution ciphers. And can I get a show of hands? Has anyone here heard of the Caesar cipher before? Oh, actually, a lot of people. Okay, cool. This is a bit of an Easter egg. Vim actually has a Caesar cipher built-in command. It's G question mark. Kind of cool. Like maybe if you're doing a presentation and that you don't want to actually hide part of your buffer, you can just ROT13 it. Anyway, so the idea is behind ROT13, ROT stands for rotation. And you can actually do that with any number. Right? I mean, really, from 0 to 26 or 25, I guess. You're just adding 13 to each number of the alphabet. So you take the letter A, and that's 0. B is 1, so on and so forth. And you add 13 to it, where you sort of have this wraparound. Once you get to Z, you go back to A, because we're kind of operating this modular arithmetic. And you have this mapping of your original plain text to your ciphertext. Just add 13 to each letter. So I'm sure this worked very well in Caesar's time because he was pretty successful. But in this day and age, this doesn't really quite cut it. And actually, this entire class of substitution ciphers doesn't really quite cut it because cryptanalysis, you can make some very strong, educated guesses based on things that you know. So you may not know the private key. And if you knew the private key, you probably wouldn't be doing analysis. But for example, in English, even on this page, of course, there are vowels. Vowels occur more frequently than consonants. And just of all the 26 letters, some occur more frequently than others. Some words occur more frequently or closer to other words than others. So English text, when you're trying to do something like that, it's not totally random. And this poses some problems for all this general class of substitution ciphers. So I think as an example here, another show of hands, anyone heard of the Enigma cipher, like the bomb in World War II? Okay, yeah. I mean, we sort of have that. Okay, well, I wouldn't say we have the Nazis to thank for computers, but I guess we have Alan Turing trying to beat the Nazis to thank for computers, because that was sort of where a lot of this original stuff towards building a computer was done. I wasn't the only person, but pretty major effort was cryptography. And for example, a lot of these U-boat messages were signed off with, I don't actually know how to pronounce it in German, potentially nothing to report. So this is what's known as a crib or a known plaintext. And this is actually used to crack the Enigma cipher, which is sort of dragged to try and find this in the broadcasts. It's kind of an interesting historical thing. It would actually get the British would bomb a specific city so they could see that city's name pop up in a report. They could sort of generate cribs. It's like pretty extreme example, but yeah. So frequency analysis, known plain text. There are some other sorts of methods you can use to break these ciphers, but generally speaking, they're not secure. We have some challenges on them that you can try out, but do not use substitution ciphers. So the sort of ideal, we're going to go from the bad, and we're going to go to the good, and then we're going to go to not the ugly, but I guess the middle ground, the compromise. So I have it in Python here. I really should put the slide, swap this slide with the next slide. So I'll do that. So we essentially have this thing called perfect secrecy. So a one-time pad is essentially just a random bit string that is the length of your plain text. And that sounds sort of abstract, but just think I just have a giant blob of randomness. And the giant blob of randomness is enough to cover whatever I want to say. You don't really have to do type juggle in there. And if I perform this operation like XOR, as we were discussing earlier, I have a completely random bit string, and I have some, plain text bit string, and I XOR them together. Unless I know something about that, unless I know the plain text bit string, because every bit is independent of each other bit, I get back effectively just a completely random bit string. So, we did it. We beat cryptography. And I'll go home. This is a solved problem, but it's not so simple, unfortunately. So again, not only are you doubling the size of your message, now you have this one-time pad and your plain text in order to,
Why are you sending the pad?
That's a good question. Why are you sending the pad? Yeah, you wouldn't send the pad along like just in plain text. Oh, okay. This is true, but you, if Alice and Bob want to communicate, that's actually a very good question. How do Alice and Bob sort of get this shared secret? How do they know? How can they agree upon this one-time pad, right? Even if they agree upon it ahead of time, for every message, essentially, Alice and Bob, maybe they meet in a back alley and they trade these two giant dictionaries, which is just full of random bits. And every time they want to send a message, they'll just take some of these bits and use them. But once you use them, you can't use them again. That's the problem with this is why the one-time pad is secure, but also that you can't reuse it. And that's kind of problematic because eventually it's going to be pretty painful to meet Alice and Bob to meet in the dark alley to exchange dictionaries all the time. Eventually the allies are going to catch on and send a spy to intercept them or something. And also it's just kind of it's just not very efficient. I mean, if you want to encrypt every packet leaving your machine, you sort of have to like double the size of that. I mean, that wouldn't be the worst thing in the world, but it's certainly not ideal. Yeah, so in crypto, I guess 2 and 3, we'll talk about PRGs, pseudo-random generators, and this is essentially how you stretch a little bit of randomness to a lot of randomness. So you have some shared secret, which is X number of bits long, maybe 1,000 bits long, or 1,000 bits long, or something like that. I mean, probably want more and more in this day and age. We're worried about Shor's algorithm, but general idea is you establish a shared secret, and then you use that you stretch that initial shared secret, have lots of pretty much random that you could use for similar to one-time pads. Okay, so now we have symmetric encryption. Did you want to talk about?
No, I can do Diffie-Hellman.
Okay, all right. So symmetric encryption, again, what we're talking about here with XOR, this is kind of, I think, probably the simplest example of symmetric encryption. Essentially, all you have is we're making, okay, this is not like great because it's just in Arial font, but we have a decode function and we have an encode function. An encode takes in our plain text and our key, and our decode takes in our ciphertext and our key and spits out our plain text. And all we're saying with decode is that I can use essentially the same key to encrypt and decrypt the message. In the case of XOR, I mean, that's literally you're doing the exact same operation. It doesn't necessarily have to be that, but that's a pretty typical example. And the difference between this and asymmetric encryption, which we'll talk more about crypto 2 on Sunday, is that you have a public key and a private key, where essentially you share your public key with other people, and people can encrypt, anyone can encrypt messages to you, but only the person with the private key can decrypt messages. So when you're trying to upload your GitHub or your SSH key to GitHub for a class or something, make sure you upload your public key. If you upload your private key, you're not going to have a good time. Well, I mean, just hope no one at GitHub has that information, I guess. There's also a good XKCD for that. Okay, so I promised we would talk about computational hardness. So this is the computational hardness slide. Again, a lot of these problems we'll talk about, including Diffie-Hellman, Elgamal encryption, and RSA are predicated on this problem called like the discrete log problem, or similarly the integer, like the prime factorization problem. Not factorization of prime, but like you have two very large prime numbers, and you want to figure out, given this composite number, what those two primes are. That's the formal statement. Essentially, if you have a to the b is equal to some x mod p, find b. So it's very easy to calculate this. It's very easy to take the exponent of a number, which is multiplication, but trying to find what b is thought to be a very, very hard problem. That being said, Shor's algorithm does kind of put this into question, but also, who's going to build a quantum computer, right? Yeah, so discrete log and factoring are kind of the two things to know. This won't be super relevant for the challenges, but just a good thing to keep in the back of your mind. Now, over to Nikhil for Diffie-Hellman.
Okay, so Diffie-Hellman is actually not like an encryption scheme. It's a technique to get a shared secret. So here's the setup. The setup is that you have two people. Each one of these people has a secret of their own that the other person does not know, and we assume that nobody else knows the secret. And they are communicating over a completely public channel. So there's no like meeting in the back alley or whatever. Like everything they communicate with each other, we can assume that like eavesdropper knows. And the problem is, in the setup, how do they achieve a shared secret? So a value that only the two of them know, and nobody else who can even like listen to all of their conversations can know. And the way you do it is there's some like modular arithmetic, kind of to summarize. There's the set of public parameters that are always the same. So there's like this base that you use for modular exponentiation. There's like a modulus for taking remainders, and then Alice and Bob will raise this base to their private keys. They will send this to each other because modular exponentiation is hard. Nobody can kind of reverse the exponentiation, so nobody can recover their private secrets. And when they get the messages from each other, they will then raise those messages to their private keys, private secrets. And just by like math exponent rules, it turns out that they actually end up with the same value, and nobody else can actually figure out what this value is. In modern implementations of Diffie-Hellman, instead of doing modular exponentiation, you would do computations over like different kinds of like mathematical terms groups, different kinds of mathematical structures. The one that's used, I believe, most cases is elliptic curves, and then you can do stuff that's like very similar to modular exponentiation, but instead of doing it with numbers, you're doing it with elliptic curves. But the idea is the same essentially. And like, I guess cases where this might be useful is if you want to send encrypted messages to each other, you actually need some key to encrypt them with, and let's say you can only talk over a public channel, how do you get such a key? You can't just send the key to each other, because then everybody knows the key. So you would do a key exchange, like with Diffie-Hellman, and you'll be able to get a key, and then once you have a key, you can use that to encrypt your messages.
Right. Oh, and just out of curiosity, why not just Diffie-Hellman our messages?
Why not just Diffie-Hellman your messages?
Yeah.
So you mean like the Diffie-Hellman, like you, wait.
Oh, no, sorry, never mind. Disregard.
The trick is, instead of the public channel, we communicate over telekinesis. And that's the way we agree on our shared secret. Okay, so this is the tool slide I alluded to earlier. Personally, the number one thing is pen and paper, unless you're factoring a very large number, in which case you'll be sitting there for quite a while. The tools for Python are going to be, again, SageMath, something called PyCryptoDome, and there is a legacy version of the PyCryptoDome library. So when you're installing that, just make sure you're installing the one that says this is the replacement of the legacy. If it doesn't say that, it's probably the legacy version. And the two do conflict if you install them both. So try not to make that mistake. And of course, Cone tools just for connecting and sending bytes to challenge server. So that's a very contrived solve script, but you can look at the SageMath docs, sort of see what functions are useful. SageMath is like a very, very, very large library. You won't nearly use everything there is to offer, but it is helpful for some of the challenges. And yeah, so I guess that's pretty much it for Crypto 1. And I just want to leave you guys with some food for thought for Crypto 2 and Crypto 3. And again, we discussed with Diffie-Hellman, how we are establishing a shared secret. So there are other methods. One we'll talk about later is RSA. Another thing is, again, how do Alice and Bob know they're really talking to each other? And how do they not know I'm just, so I'm saying I'm Eve and I'm claiming that I'm Bob. Essentially, I'm fooling the postman delivering the letters to even if I don't know, that they're shared secret. Maybe Alice is establishing a shared secret with the wrong person. So this is this idea of digital certificates, which is what's used on kind of the World Wide Web, or if you use GPG, maybe the Web of Trust. Yeah, so the one thing that our duty to remind all people: do not roll your own crypto. Repeat after me: do not roll your own crypto. That was weak sauce. Please, one more time. You guys sound like you're going to roll your own crypto. You know that? Don't roll your own crypto. Thank you, Ronan. Okay. You've been warned. I'm serious. Okay. So in addition to the challenges on Pony CTF, there is a fantastic resource called CryptoHack. I'd say this is probably one of, if not the best, cryptography resources, especially for CTF, that are out there. Again, it's completely free. They have their own kind of set of lesson modules mixed together with challenges, kind of like an interactive notebook programming type of beat. And you can actually get points for doing these challenges on CryptoHack. You can get points for those on Pony CTF. So you're not necessarily at a disadvantage. Actually, I think some of those challenges don't really have that many solves. So if you're looking to get ahead on the leaderboard, try out CryptoHack. Yeah. I want to talk about which challenges we have up.
Yeah.
So yeah, we have a bunch of challenges up for this meeting. Did you actually publish them yet?
No.
Okay. So yeah, those should be up soon. We have there's a couple that are like XOR stuff. Those might be good to start with. There's one on there's a couple on Diffie-Hellman. So there's one that's actually pretty good for kind of understanding the computations that happen in Diffie-Hellman. It's basically going to have you do the Diffie-Hellman like key exchange yourself with some parameters that they give you. There's a couple on this thing called AES. We will not cover this today. It's a another kind of cipher. It's a block cipher. If you're interested, you can maybe like try looking at the Wikipedia page for that or something. They aren't too bad. Should be doable. And then we have also a couple of challenges in RSA. So RSA is asymmetric encryption. So like public key, private key, stuff like that. RSA actually is going to be covered in Crypto2, which is this Sunday with Richard and Emma, I think. So if you kind of want to get a head start on that, you can look at those. Easy RSA actually I think isn't too bad. Might kind of be fun to do. And yeah, I think that's pretty much it. The Vault, of course, has a bunch of others, and I think there is one challenge on one-time pairs. Is that true, George?
One challenge on what?
One-time pairs?
I believe so, yeah.
Okay.
Or all these challenges are currently on the vault. I have to move them to the regular meeting section, so they're all accessible. But yeah, I think pad.
Yeah.
Yeah.
Okay, so that's one-time pairs. But yes, there's a pretty good mix of challenges, and the Vault has many more if you're interested. And that's Crypto have for more stuff. Yeah.
Oh,
Okay, so yeah, next meeting's Crypto2 is this Sunday. So Crypto2 is RSA is AES in Crypto2?
it's Crypto3.
It's Crypto3. Okay. But yeah, so like if you enjoyed this stuff, come to Crypto2 on Sunday. If you did not enjoy this stuff, still come to Crypto2 on Sunday, because like you might enjoy it. Next Thursday is Halloween. Are we doing anything? Well, we're just gonna
I don't think so.
TBD. Okay.
Keep you updated.
And next Sunday is actually like some really fun stuff. This is like actual like hacking. With so yeah. So if you like Rev 2 and Cone 1, this should be a lot of fun. This is like how to get a shell on someone's computer, pretty much. Not that you should do that actually, but yeah.
You should do it on our servers.
Yeah, you have permission.
You have permission to do it on our servers. Yeah.
Yeah, can I just talk with Shell ESXi real quick?
Oh, no.
Oh.
By the way, the flag is the flag is not to do, but no. How do we move challenge out?
Sorry, I'll be like a surprise windows.
Technologically.
Yeah, spare yourself.